Laptop charger, the tiny power plant in your bag. You finally buy your dream laptop. It's thin, it's elegant. It almost disappears between your fingers. Then you reach the bottom of the box. And there it is. A chunky, ugly black brick. It's heavy. It heats up. It takes half the space in your bag. And it raises a simple question. Why does something so small need something so big to power it? Here's the surprising part. That ugly plastic brick may actually contain more complex power electronics than the laptop itself. Inside that box is a miniature power plant, translator, and security system all working together. Today, on Simple Things, Surprising Histories, we're opening up the mysterious black brick, the laptop charger. Chaos from the wall. To understand the charger, we need to start with your wall outlet. The electricity coming from the wall is actually a bit of a wild beast. It's called alternating current, or AC. Instead of flowing smoothly in one direction, the current changes direction 50 to 60 times every second, and the voltage is huge. In Turkey and most of Europe, 220 volts. In the United States, 110 volts. Imagine trying to wash your hands using a firefighter's hose. The pressure is enormous. The flow constantly shifts. Your laptop, however, is extremely delicate. Its processors and circuits need something very different. A calm, steady stream of electricity called direct current, DC, usually around 19 volts. If you plug 220 volts of AC directly into your laptop, the motherboard would fry instantly. Smoke. Dead laptop. That's why the charger exists. Its job is to take the chaotic electricity from the wall and translate it into something your laptop can safely understand. And it does this in 3 clever stages. Stage 1. The bridge rectifier. Forcing one direction. The first component electricity meets inside the charger is called the bridge rectifier. Imagine a busy intersection with 4 traffic police officers. Cars are coming from different directions. No matter where they come from, the officers redirect every car into the same lane. That's exactly what the bridge rectifier does. AC electricity moves back and forth. The rectifier flips the negative waves upward, forcing all the current to flow in one direction. But there's still a problem. The electricity is now moving in one direction, but it's still bumpy and unstable. That's where the next component enters the story. The capacitor. You've probably seen them before. Small cylindrical components that look like tiny soda cans. A capacitor works like a water reservoir. When electricity spikes, it stores extra energy. When electricity dips, it releases stored energy. The result? The rough pulsing current becomes a much smoother flow of power. But we still have one big issue. The voltage is still far too high. We need to go from 220 volts down to about 19 volts. Stage 2. Switch mode power supply. The shrinking trick. Old power supplies solved this problem using massive iron transformers. If your charger used that old technology today, it might weigh 2 or 3 kilograms. Instead, modern chargers use something much smarter. A switch mode power supply, or SMPS. Inside the charger, a tiny transistor begins doing something incredible. It rapidly turns the electricity on and off. Not once per second, not 100 times, but tens of thousands of times every second. Yes, your charger is constantly chopping electricity into tiny pulses. Why? Because physics has a fascinating rule. When electricity is switched at very high frequencies, the transformer used to change voltage can be made much smaller and lighter, instead of a heavy iron block. You only need a small component that fits in the palm of your hand. So your charger isn't just passing electricity through, it's rebuilding it thousands of times per second. The secret guardian. The optocoupler. Now we reach one of the most fascinating parts of the charger. A tiny device called an optocoupler. This component acts as a safety barrier between 2 worlds. The dangerous high voltage side, the safe low voltage side connected to your laptop. These 2 sides must communicate, but they cannot touch. So how do they send signals? With light. Inside the optocoupler, electrical signals are converted into a tiny beam of light. That light crosses the barrier and tells the circuit on the other side what to do. If the voltage starts rising too high, the optocoupler sends a message back to the switching transistor. Slow down. All of this happens thousands of times every second, silently protecting both your laptop and your hands. It's the charger's invisible security guard. Why do chargers get hot? You may have noticed something. Laptop chargers often get warm, sometimes surprisingly warm. That's because no power system is perfectly efficient. Every time electricity is converted, switched and transformed, a small portion of energy is lost. That lost energy becomes heat. Cheap chargers can waste a lot of energy this way. Better chargers use more advanced components to minimize those losses. And recently, a new technology has started changing charger design entirely. The new generation, GaN chargers. Many modern chargers are now using a new semiconductor material called gallium nitride, or GaN. Compared to traditional silicon, GaN can switch electricity faster and more efficiently. That means smaller chargers, less heat, higher power. That's why some new laptop chargers today are shockingly tiny, yet powerful enough to charge multiple devices at once. The black brick is slowly evolving, so the next time you toss that charger into your bag and sigh, take a moment. Inside that little plastic brick are high-speed electronic switches, energy reservoirs, microscopic transformers, and safety systems communicating with beams of light. Every second, it takes the chaotic electricity from your wall, cuts it apart, reshapes it, and rebuilds it into the precise power your laptop needs. That ugly brick in your bag? It's not just a charger, it's a miniature power plant. Until the next time we open up another ordinary object and discover the extraordinary engineering hidden inside.